This is section 13.2, and this is example 7. And prior to doing example 7 in our notes, we're going to introduce the idea of a line integral of a vector field. So we did vector fields in section 13.1. And a vector field is simply just, a field that at every point in the plane produces a vector, and from that vector we get a field, and it gives us an idea of a particular um, movement of a surface or whatever the case may be. And so in this case, what we're going to do is we're going to actually look at what happens in a vector field if we were to pass a particle through it. So I'm just going to refer to example 7 really quick in this picture. So here's a vector field in blue, and we have a path that goes through it. And this particular path is moving in the direction from the point 1, 0 to 0, 1. And if you think about just the movement of this path and where these vectors are pointing, our path goes through the vector field sort of in the opposite direction. And so think about if this was like a river or something where these vectors were showing the current, and you had an object, a canoe, let's say, that was trying to travel along this path. You'd have to do a fair bit of work to get from our starting point of 1, 0 to the end point of 0, 1, just because you're going against the current. So that's what we're going to talk about in this next little section for section 13.2. And here are formulas. And my goal is to try to give you a quick idea of where these formulas come from. But really, and unfortunately, there are 3 formulas for this. We're going to primarily use this middle one here, so you don't have to necessarily compute the other 2, but you do have to know what the other 2 are asking, because all 3 of them are asking exactly the same thing. A couple things just to point out. Number 1, in this first formula, you have capital F. That is a vector, and again, with Stewart's book, he bolds it. He doesn't put any kind of vector notation above it. So that's a vector field. R is also a vector, and R is going to be based on the path that we take. The middle one is the most common one that we use. We're going to take our vector field, which is going to be made up typically of x and y, and we're going to use the path in the vector field, and then we're going to multiply by the derivative of that path. This is the one I'm going to show you, I think, so you can see where it comes from. This one is also interesting because it connects to what we've done so far. What we've done so far is we've integrated with respect to arc length, which is ds, and t is going to be the unit tangent vector. And the reason that that's going to be helpful is really what I'm going to show you next, which is a little picture of what's going on here. So imagine, if you will, just a path, some general curve like this, and if we were to take a little section of this, so just a little piece of it, and sort of project it out and blow it up, just so we can analyze it a little bit more. Let's say that this particular curve was going in this direction. So we're going from, let's say, just capital A to capital B. If we were to sort of zero in on a point on this little section here, let's say that we're right about there, and let's say that we look at specifically the force vector. So from our vector field, let's say we look at the force vector F at that particular spot, and we compare that to the tangent vector at that particular spot. So this is going to be the unit tangent vector. When we think about this, we're looking for what type of work is done by moving this little object along the curve through the particular vector field. And if you remember, your work formula is simply just the force multiplied by the displacement. And in this case, our displacement is going to be essentially the movement of that tangent vector along the curve. And what we're going to do is we're going to think about it in terms of arc length. So instead of displacement, what we're going to do is take the unit tangent vector multiplied by sort of the change in the actual arc itself. And to get a good picture of this, we're going to make that change really small. So that delta S, that delta arc length, that change in the arc length, we're going to make really small. But if we think about it, the displacement at that particular point along that curve is really just a slight movement along the curve in the direction of the tangent vector. However, the force is going to impact what type of work is done. Okay, so if we sort of convert this idea that we're talking about into a line integral form, and we were to do this throughout the entire curve, we're going to take the force dotted with the unit tangent vector, and delta s, the change in the arc length, is going to be ds, which is going to be our variable that we're going to integrate in terms of. Now, this is really what you're going to see as that formula over on the right side of this equation. So hopefully that makes a little bit of sense of where that maybe comes from. From there, we can do a variety of just kind of substitutions here to get our equation in the middle. So if you remember, the tangent vector is the vector r prime divided by the magnitude of r prime. And so if we think about that from way back when, and then we also think about ds. ds is the magnitude of r prime times dt. So if we were to take this equation that we got for our line integral, f dotted with t ds, and we were to do this substitution, we have the line integral of the vector field f dotted with t, which I'm going to write as r prime divided by the magnitude of r prime. And then we have ds, which is going to be the magnitude of r prime dt. And if you notice, our magnitude of r prime will cancel, and what we're left with here is the line integral of the vector f dotted with r prime, and it's going to be in terms of dt. So that's going to show this middle equation, which we're going to use most often. So that's a little bit about where it comes from. Okay, let's try an example. Now the work done, and remember all those three equations that we just talked about, all three of them really is calculating work. So if it says find the work done, what we're looking for then is the line integral c over c of f dotted with the derivative of r of t dt, or any one of those ones that we were writing. Now remember, we have to, and maybe let me rewrite this just slightly. We have to put in the place of that vector f, we have to put in r of t, which is going to be the path that we're analyzing. So right now, if you refer to the question, we have the vector field f, which is made up of x squared negative xy, and so we're gonna take what the path is, which is r of t, and we're gonna substitute it in here so that we have a more appropriate vector field representation in terms of t. In other words, we want to know what the vector field f of r of t is, and since r of t is cosine t, which that's going to be our x component, and sine of t, that's our y component, we get, so instead of x squared, we're going to put in cosine of t and then square it. So we have the vector cosine squared t. And then instead of minus xy, we're going to have negative cosine t sine t. And this is going to represent our vector field with the curve itself substituted in. Okay, then what we need to know is what is the derivative of r, which is easy. That's going to be negative sine t and cosine t. And I think what we can do now is set up our integral. So our integral would be when t is 0 to pi over 2. And again, we have the picture over on the right side, so we're going to take this path, we're going to pass it through the vector field. And by the way, just think back to what I was saying at the beginning of this. Based on the direction of our vectors that we have, our path is passing through in this behavior, in this pattern. Do we think that the work being done is going to be positive or negative? Well, if the path works with the vector field, then the work will be positive, and if it works against the vector field, the work will be negative, and if it works perpendicular to it, then the work will be 0. And that goes back to the dot product formula. So if the dot product between two vectors is 0, then they're going to be perpendicular. So we should get a negative value for this particular answer because our path is working against the vector field. Okay, so let's go ahead and excuse me. Let's go ahead and set this up. We have the vector f of r of t, which is cosine squared t, comma negative cosine t sine t, and we're going to dot that with the derivative of r, and our variable of integration is t, so we have dt. And then we're going to perform the dot product, so we have 0 to pi over 2 of cosine squared t times negative sine t, so that's going to be negative cosine squared t sine t. And then we're going to add a negative, so minus cosine squared t sine t. And just as a quick review, just so you know where I'm going with this, so we have cosine squared t, that component times the first component in the second one, that gives us this value, and then we add this one times that one, and that's going to be our dot product. Okay, and this combines, so what we get is negative 2 of the integral 0 to pi over 2 of cosine squared t sine t dt. All right, from there we need a u substitution. So we have cosine of t as u, and du is negative sine t dt. And the negative is good. We have a negative there, so we're going to use that as our substitution. We get 2 times the integral. I'm not going to deal with the limits right now. Times u squared du, which is 2/3 u cubed. That converts to 2/3 cosine cubed t from 0 to pi over 2. And cosine of pi over 2 is 0, so what we have is 0 minus 2/3 times 1. And there we go. Our answer is negative 2/3, which again should make some sense because the path was working against the vector field, so the work done is going to be negative. Hopefully that makes some sense. This is example 7. Next video we will do example 8.